Namaskaram. In this session, we will see the evaluation of triple integration in cylindrical coordinate. The solution of last homework. Okay, we consider a point in 3D space and how to represent this point, the coordinates of this point in cylindrical coordinates. In cylindrical coordinates, we use r, theta, and z. R and theta is same as from our polar coordinates. Okay, that means first you take the projection to xy plane and you consider this distance. We know that this distance is our r. And what is theta? Theta is the angle measured from positive x-axis. Okay, using r and theta, you can identify this projection. Then using one more quantity z, you can locate the point in 3D space. That's the idea of cylindrical coordinates. Okay. In the introductory session of triple integral, we have seen that the definition of triple integration over a solid. Okay, this is the definition. Actual definition is limit n tends to infinity, sigma k equal to 1 to n, this into delta vk. And what is delta vk? First of all, the procedure is, first of all, we subdivide our solid G using planes parallel to the coordinates planes. That means we use x equal to constants, y is equal to constants, and similarly z equal to some other constants. Okay, using such planes, you can subdivide the solid as a small rectangular pieces. Then suppose we assume that there are n such rectangular pieces, n such cuboids, and delta vk is the volume of that cuboid, and this point is an arbitrary point from the kth cuboid. Then you consider this sum, then take n tend to infinity. This is the process. Okay. Similarly, in the case of cylindrical coordinates, instead of x equal to constant, our r equal to some constant, and instead of y, our theta equal to some constant, and let it be r1 and theta 1, better like that. And for z equal to some z1 like that. Okay, so we are going to subdivide our solid using surfaces like r equal to r1, theta equal to theta 1, and z equal to z1. Such surfaces. So you can subdivide the solid. How? Okay. So we consider a specific region. What is theta equal to theta 1? In 2D, we know that theta equal to theta 1 is a ray like this. But in 3D, it's like a plane. Okay. Similarly, theta equal to theta 2. And what is r equal to r1? In 2D, r equal to r1 is a circular region. Okay. In 3D, it's a cylinder. And similarly, r equal to r2. And z equal to z1 is a plane passing through this point and parallel to xy plane. And z equal to z2 is another plane passing through this point and parallel to xy plane. So what about the intersection? The intersection of all these things gives almost like a solid like this. And this solid is called a cylindrical wedge. Okay, that means in cylindrical coordinates, we are going to divide the solid using cylindrical wedges. Okay. Suppose our G contains n such cylindrical wedges. Okay, suppose you divide G using r equal to constant and theta equal to constants and z equal to constant. So there are so many cylindrical wedges inside G. Suppose there are n such cylindrical wedges. Okay, then similar to our Cartesian triple integral, we can define the triple integral in r, theta and z using the same formula. Okay, limit n tends to infinity, sigma k equal to 1 to n, f of r k star, theta k star, z k star, delta vk. And what is delta vk? Delta vk is the volume of the kth cylindrical wedge. Okay, so next task is to find this volume of cylindrical wedge. Okay, the evaluation of volume of this cylindrical wedge is very easy. We choose a center point like this. Then how to find the volume of a shape like this? This is nothing, that is base area into height. Okay, and what about the base area? You take the projection. It is clear that this shape is familiar, and this is a polar rectangle. Okay, we know that the area of a polar rectangle with these conditions are nothing, rk star, delta rk, delta theta k. Okay, so height is nothing, height is the delta zk. So that is change in z. Okay, so delta vk equal to delta ak into delta zk. And what is delta ak? That is rk star delta rk, delta theta k into delta zk. So we can approximate delta vk using this formula. Okay. Okay. Then we can substitute delta vk in this formula. So this becomes limit n tends to infinity, sigma k is equal to 1 to n. this into, instead of delta Vk, this is Rk star, delta Zk, delta Rk, delta theta k. Okay, then what is the triple integral notation of this representation? As per our previous results like that, we can write this infinite sum is like this. Triple integral or the corresponding limits f of r theta z, this become r dz dr d theta. Okay, so we can write our triple integral in cylindrical coordinates like this. Okay, so next we have to identify the limits of z, r and theta. Okay, so to find the appropriate limits, we know that suppose this is our solid G and bounded by z equal to g1 of r theta. So lower bound is this surface, upper bound from g2 of r theta, and theta, and this is projection is r. We denote the projection by r. Okay, so we have to integrate over the solid using cylindrical coordinates. So we have to identify the limits of z, and this is limit of r, limit of theta. To identify the limit of z, that is very easy. You consider a vertical strip like this. And it is clear that the lower value of z is always from this surface. That is, the lower value is g1 of r theta. Right. And what are the upper value? Upper value of g2 of r theta. Then, to cover this entire solid, we have to move this vertical strip along the surface. That means along this projection. Okay, along this projection means we have to identify the range of theta and r. It is clear that r is varying from this point to this point. This is the range of r. So lower value of r is in terms of theta, that is r1 of theta, and upper value of r is in terms of theta, that is r2 of theta. Okay, again, to cover this region r, theta should varying from theta 1 to theta 2. So theta 1 to theta 2. So this is the iterative integral representation of this triple integral in cylindrical coordinates. Okay. Okay, then we can conclude everything using this result. G be a solid bounded above by the surface and below by this one. The projection of the solid on xy plane is a simple polar region R. Then the triple integral over G dV in terms of cylindrical coordinates is like this. Okay. Use triple integration in cylindrical coordinates to find the volume of the solid G that is bounded above by the hemisphere z is equal to square root of 25 minus x square minus y square, below by the xy plane, and laterally by the cylinder x square plus y square equal to 9. Okay, so first we have to sketch this solid. So laterally by the cylinder x square plus y square equal to 9, and its top is bounded by hemisphere z is equal to, okay, why it is hemisphere? If it is square, you just simply square it. What happened? This is z square equal to 25 minus x square minus y square. We can write this as x square plus y square plus z square equal to y square. This is the equation of a sphere. Okay, then why it is hemisphere? Because here z is always positive. So the upper portion of the sphere, that's why this is a hemisphere. Okay, so what about the intersection? So the solid is like this. The top is bounded by our hemisphere z is equal to square root of 25 minus x square minus y square, and side is bounded by our cylinder x square plus y square equal to 9. Okay, so we have to find the volume of the solid. So how to set up the integral? Okay, so volume is equal to triple integral over G 1 dV, that is equal to triple integral R. In cylindrical coordinates, this dV become R dz dr d theta. So this is the range of z. It is clear that our z is starting from xy plane up to the sphere. Okay, so lower value of z is 0, and lower value of z is 0, and what about the upper value? Upper value from the sphere, that is square root of 25 minus x square minus y square. So this is the upper value of z. Next we have to integrate over r. Integrate over r means the projection. So this is our projection, the circular region. Okay, so what is the radius of the circle? We know that the circle is from this is the intersection of cylinder x square plus y square equal to 9 with xy plane. So it is clear that its radius is also 3. Okay, so its radius is 3. Clear. We have to cover this region. We have to integrate over this region in polar coordinates. That means, what is the range of R? R should varying from this point to up to boundary. So what is the lower value of R? R equal to 0 to R equal to 3. Right. So R is varying from 0 to 3. Then to cover this region, what is the range of theta? We have to cover this entire circular region. So theta should varying from, this is theta equal to 0, theta equal to 0 to theta equal to 2 pi to cover this region. So 0 to 2 pi. So this is the corresponding cylindrical representation of this integral. Okay, now you can easily integrate this one. Okay, this become integral 0 to 2 pi, integral 0 to 3. This r is constant with respect to z, so this become r z 0 to square root of 25 minus x square minus y square dr d theta. Next you have to substitute upper limit and lower limit for z. So this become r into square root of 25 minus x square minus y square. When z equal to 0, the time is 0. Okay. Next you have to integrate with respect to r. So before integrating with respect to r, we have to convert this in terms of r and theta. Okay. So it is clear that we can write this as 25 minus x square plus y square. Then what is x square plus y square in polar coordinates? That is r square. So this becomes 25 minus r square. So this is equal to 0 to 2 pi, 0 to 3, r into square root of 25 minus r square dr d theta. Okay, for integrating this with respect to r, we make a substitution. That is u is equal to 25 minus r square. So du is equal to minus 2r dr. For r dr is equal to minus du by 2. So this portion become, okay, so integral becomes 0 to 2 pi integral, and our square root of 25 minus r square becomes square root of u, and r dr become minus du by 2 d theta. And what is the limit of u? Okay, we know that r is varying from 0 to 3. So our u, what is u? U is 25 minus r square. When r equal to 0, this becomes 25. Right. So lower value is 25. And when r equal to 3, this becomes 25 minus 3 square, 25 minus 9, that is 16. Okay. So r is varying from 25 to 60. Okay, this is u raised to 1 by 2. Its integration is u raised to 3 by 2 by 3 by 2. That is 2 by 3. Okay, d theta. And its limit is 25 to 60. So this becomes 0 to 2 pi. And you can cancel these two. So minus 1 by 3 into, when u equal to 16, this becomes 16 raised to 3 by 2 minus 25 raised to 3 by 2. And what is 16 raised to 3 by 2? First you have to take the square root of 16. That is 4. Then 4 raised to 3. That is 64. Okay. Minus 25 raised to 3 by 2. So first you have to take the square root of 25. That is 5. Then 5 raised to 3. That is 125. Then this is equal to integral 0 to 2 pi minus 1 by 3 into 64 minus 125. That is minus 61 d theta. So this is integral 0 to 2 pi 61 by 3 d theta. This is equal to 61 by 3 theta 0 to 2 pi. This is equal to 61 into 2 pi. This is 2 pi by 3. That is equal to what? That is equal to 61 to, that is 122 pi by 3. So this is the volume of this solid. Okay. So this is the volume of this solid, 122 pi by 3. Yes, 122 pi by 3. And one more thing, actually we use here square root of 25 minus x square minus y square. Instead of in Cartesian form, you can use its polar form. No problem. You get the same answer. You will get the same answer. That means you can use like this: 25 minus, what is our x square plus y square? That is r square. So you can integrate like this. This also gives the same answer. Okay. Okay, this is your homework. Thank you.